Okay, so the story of Tycho and Johannes Kepler continued. So at the end of the last video, I was telling you that after the meal with the king, then in his new country, Tycho ends up dying, and they think it's because his bladder ruptured or something, and he from not getting up to urinate when he needed to. So he dies, and now Kepler wants all the data. And Tycho's family knows that he did not want it to give it to Kepler, so they refuse to give it to him. Kepler insists. He even takes him to court. And in one of the things I read, it says, in the end, Kepler gets his hands on the data by less than honorable means. But they don't say what that less than honorable means is. But Kepler does get the data. And as soon as he gets all the data and sees it, Tycho Brahe was right. Kepler figures out what the planets are doing, and he comes up right away with his 3 laws of planetary motion, which is what we're going to look at in a second. But just before then, another little interesting side note is that probably about 40 years ago now, I think it was the 1980s, Denmark decided to dig up Tycho and his wife where they were barren and bring them back to Denmark to make he was a famous astronomer. They were thinking we can bring him back, we can give him a burial spot, put a big monument there, tourists will come. And so they do. They dig them up. They open Tycho's, casket or whatever it is he's buried in, and there's the gold nose, so they know they have him. And because it was a time when you could do DNA testing, they took some DNA samples. And when they ran the tests, they found something really interesting. They found extremely, extremely high levels of mercury in Tycho's body. Higher levels of mercury that were so high that he could not have accidentally ingested it. It would almost have needed that to be that someone had been feeding him mercury a little bit each day for the course of a year or so. Did I mention that Kepler worked with Tycho for about a year before he died? So the present day theory is that Kepler poisoned Tycho to get the data. That does not change the name of Kepler's 3 laws of planetary motion. It doesn't even give a little asterisk with, with thanks to my good friend, good buddy Tycho for all the 40 years of star charts. There's a great book, if you are bored in these times, that you might want to read. It's called Heavenly Intrigue, Johannes Kepler, Tycho Brahe, and the Murder Behind One of History's Greatest Scientific Discoveries. And it lays out how it had to have been Kepler that was poisoning Tycho all along. So I tell you this story just because I think Tycho, after 40 years of star charts, he has a right to get, at least an honorable mention here. All right, so now Kepler's 3 laws of planetary motion. The first law is actually pretty straightforward, and it's simply that the orbit of all planets around the sun are mathematical curves called ellipses. And I think you would have done ellipses in grade 11 math, maybe, called ellipses, with the sun at one of the 2 focal points of the ellipse. One of the 2 focal points of the ellipse. So if you think of a circle, right? So here's my circle, and it has a center point. If you put your hand on the top of the circle and the bottom of the circle and you squish, the circle is going to become an ellipse. And as you squish, this center point separates. It almost like it undergoes mitosis or meiosis or something, and it separates into 2 points. So the further you squish it, the further these 2 points go apart. These 2 points are called the focal points. And the distance between these 2 points is D. And then an ellipse has a major axis, which goes this way. So this is the major axis, which is L. It also has a minor axis, which runs the other way, but which they would have told you in math, but we don't care about in physics. And so the flatness of the ellipse is something that's known as the eccentricity. It's a small e. And it's simply equal to the distance between the focal points over the length of the major axis. Okay? In other words, little e is equal to d over L. Now, just a couple of notes. Kepler saw it right away when he looked at all of Tycho's data. The reason Tycho couldn't figure it out is because Tycho and everybody else at his time was convinced that the planets had to be moving, everything in the sky had to be moving in circles. Circles were seen as the perfect shape. There is no way the creator of the universe would have used anything other than circles. It's kind of like writing with your right hand is what everyone should do, and anyone who writes with their left hand is obviously possessed by some demon. So, like, Tycho, because he was so tied to church and state, he couldn't see that the planets and other bodies were moving in ellipses because they had to be circles. Kepler, who wasn't tied to that, took one look at all the data and saw the ellipses right away. Okay? Now, the eccentricity. So it's known as the flatness of the ellipse. The bigger the eccentricity, the flatter the ellipse will be. The smaller the eccentricity, the rounder it will be. That should make sense, right? Because the more I squish this, the bigger d will become. And the less I squish it, the closer d goes to 0, and the rounder the shape is. The eccentricities actually range from 0 to 1. If it's 0, it means the two focal points are right on top of each other, and this shape is a circle. The upper limit would be when d was all the way out at the end of the major axis, right? If you keep squishing this and squishing this, it'll come to a point where d will be right out at the ends, but d could never be bigger than L. At most, it could be equal to L, and that's when you get 1, and that would be a line. Okay, so all of the planets move around the sun in these flattened circles then, with the sun centered at one of these focal points. So any ideas of like how eccentricity, by the way, eccentricity and eccentric are connected. If we talk about someone who's eccentric, it means they're not well-rounded. And so you can see that they're connected. Any ideas of the eccentricity of like the Earth, or which planet might be the most eccentric? If we were in class, I would get you to guess a bit about the eccentricities. Like, do you think they're closer to 0, closer to 1? Do they go in some kind of range? Like, so here's the sun, and then we have Mercury, Venus, the Earth, Mars, Jupiter, Saturn, and yes, Neptune, Uranus, and Pluto, and yes, I keep Pluto up there. Some people might think that maybe the closer you are to the sun, the rounder you would be, and the further you are away, the flatter, and they should go in order. It's not true. They're really quite random. And they're not very eccentric. The guy that's the most eccentric is Pluto, and Pluto's eccentricity is 0.2482. Mercury, I believe, just got to double check here, is the next one. Venus. Yeah, Mercury is the next one, and it's 0.2056. So clearly they're not going in any kind of order. So these two are the biggest have the biggest eccentricities, but they're still closer to a circle than they are to a line. Venus has the smallest eccentricity. This guy is 0.0068. So he has the smallest eccentricity. And next up would be, and I put